Hi students, I am going to talk about molecular polarity in this short little supplemental video, and this should help you guys on your quiz. So the first type of molecule that we looked at with the tetrahedral bond angles or the tetrahedral geometry was methane, and that is drawn like this, with these two bonds being regular, and those are in the plane of the paper, and this hydrogen coming out at you right here is drawn with a wedge, and the hydrogen that's pointing back into the paper is drawn with the dashed lines. And these bond angles were all 109.5 all the way around. And when we were looking at molecular polarity for this molecule, what we said is that the electronegativity of carbon was 2.5 and hydrogen was 2.1. So if we did 2.5 minus 2.1, we came up with 0.4, which qualified as nonpolar. So we don't have any polarity in any of these bonds, so the molecule as a whole is not polar. You have to have some kind of polarity somewhere. So we don't draw any dipole moments or any delta negative or delta positive symbols to indicate partial negative or partial positive. Now, what happens if we replace all of the hydrogens with chlorines? Well, we get a structure like this where all the chlorines are the little yellow beads. And with CCl4, we still have a tetrahedral structure. So all the bond angles are still 109.5, but we do have polarity when we take a look at each bond individually. Now the electronegativity of carbon is again 2.5 and chlorine is 3.0. So if we did 3 minus 2.5, we'd have 0.5, and that qualifies as polar. So chlorine is trying to pull the electrons towards itself. So this chlorine up here is saying, give me these electrons. But all of these chlorines down here are pulling back this way, saying, no, no way. And when this chlorine over here tries to pull the electrons out towards itself, all of these chlorines over here are pulling back and saying, the same thing happens with this one and this one. So we have the same pull all the way around this molecule. So even though it looks like we have polarity there, we don't, because of the electronegativity of the atoms on the other side. So there's no net dipole in this molecule. This molecule as a whole is nonpolar, even though it looks like it is polar, and that's because of the geometry of it and the opposing atoms' electronegativities. Now, what happens if we have a carbon in the center and two of the atoms it's bonded to are chlorines and two of them are hydrogens? Well, if we look at this molecule right here and assume that the chlorines are green this time, last time the little beads were yellow, but this time we've got little green balls for our chlorines, and black for carbon. Right here we can see these are in the plane. This hydrogen's pointing out at you and that hydrogen's pointed back. If we look at each individual bond, we'll remember that the hydrogen-carbon bonds are nonpolar, so we won't write anything there. But the chlorines are more electronegative than the carbon, so they like to pull the electrons towards themselves. So you have this chlorine pulling this way and this chlorine pulling this way. Now, both of these chlorines are trying to pull out towards themselves, and that is not going to work when we're talking about direction like that, because they're going to cancel out, but both of them are pulling out in this direction, which adds up. So if we were to draw the dipole moments for each of these bonds, it would look like this. And remember, you can draw the dipole moment on top or on bottom and right or left, either way you want. And how that adds up is a net dipole moment for the molecule that looks like this. The positive end of the hydrogen is the molecule's over here, and the pull on the electrons goes right through the center right here. So this would be the net dipole moment, whereas these are the dipole moments for each of those bonds. The net dipole moment looks like that. Now remember, you'll also see it as a dashed line sometimes, and sometimes instead of seeing it going through the middle of the molecule, you'll see it off to the side, and that's valid too. What we'll also see is instead of a dipole moment, we'll see the little delta symbols. So this is telling you that this end of the molecule is partially negative, and this end of the molecule is partially positive. Now what happens if instead of drawing the molecule like this, we draw the molecule like this? Well, that means that the dipole moment will point in another direction, but it will still point between the two chlorines like that. Now you see I've drawn the net dipole moment off to the side. So I could draw it right here, or I could draw it going directly between those two chlorines, or I could draw it off to the side here, or I could put the delta positive symbols over here and the delta negative symbols over here. But we must indicate that we have partial negativity where the chlorines are and partial positivity where the hydrogens are. Okay, so our next example. What happens if we have 3 chlorines and 1 hydrogen? Well, all the chlorines are going to try to pull the electrons towards themselves because they're more electronegative than the carbon. And this bond up here, we're not going to take a look at that because we decided that that's nonpolar. Now, each of these chlorines is pulling down a little bit and out towards itself. Now the out components, say we're looking at this chlorine right here. It's trying to pull out this way, but these 2 chlorines on the other side are pulling back this way, and they're saying, nuh-uh. And this guy's trying to pull out towards itself, but these 2 on the other side are pulling back and saying no. So the out components that happen are canceling out, but the pull down a little bit on each one of these is adding up. So that means that this end of the molecule is partially negative, which creates another pull. Okay, so that one right here is partially positive up here. And I've written it with the delta symbols down here and the delta positive up there. Now we could also write the dipole moment off to the side, but remember, again, you wouldn't write both of these. It's one or the other. You could put the dipole moment over here, or you could put the dipole moment right in the center of the molecule, indicating that it's pointing down like that. Now, if you turn the molecule over and you drew it like this, would that be okay? Yes, but what would happen to the dipole moment? It would flip up like that because we have to point in the direction that the electrons are being drawn on the molecule. So they're being drawn up this way towards the chlorines. Now, our next example is ammonia. So we've got NH3 right here. So right up here, we've got the lone pairs. Now, nitrogen has an electronegatividity of 3, and hydrogens have electronegativities of 2.1. So the difference there is 0.9. So these are definitely polar bonds. And it's the nitrogen in the center that is pulling the electrons towards itself. So we could draw dipole moments like this, where the arrows were all pointing into the nitrogen. Or we can just put the partial positive symbols down here to indicate down on this area of the molecule it's partially positive and the electrons are flowing up towards the nitrogen, which is going to be partially negative. Now you can see I drew the dipole moment off to the side over here. You could put it going right up the center of the molecule like that, or off to the side like that. Now what would happen if I turned it upside down? Well, the dipole moment would turn upside down too, to indicate that we had flow of electrons towards the nitrogen. Okay, you guys, I hope that helps you on your quiz, and I will see you soon. Bye-bye.